Let's move on to our next topic, fixed income valuation. The concepts we'll be discussing are very important for understanding the factors that determine the value of debt securities and their various yield measures. In this first part, we shall study the use of time value of money principles in pricing bonds. We start with understanding what market discount rate is and how to use it to derive the price of a bond. The inverse of this process is to use a bond's market price to calculate its yield to maturity. We also study the factors that influence the movement of a bond's price when its yield changes. And we end off learning the more fundamental approach to pricing bonds using a series of spot rates. Let's get started. Bond pricing is an application of discounted cash flow analysis. We know that for a cash flow of $100 1 year from now, its present value is $90.91 if we discount it by 10%. This principle is applied to bond pricing. For a 5-year $1,000 par, 10% coupon annual pay bond, its price can be calculated by summing the present values of all the bond's promised cash flows. At issuance, if investors determine the required rate of return for the bond is 10%, we say that the market discount rate for the bond at this instance is 10%. So, if we use 10% rate to discount the future cash flows and add them all up, we get a price of $1,000. To calculate this value, simply add up all the future cash flows discounted by the appropriate factor. Alternatively, you can use the TVM calculator. Enter 5N, 10IY, 100 PMT, 1000 FV, and compute PV on your calculator. You should arrive at the same figure, and that's $1,000. Notice that this is the same as the par value. This should not surprise us, as the coupon rate determined at issuance is usually matched up to the market discount rate. However, as time goes on, investors can change their view on the required rate of return for them to be invested in the bond. This is primarily due to factors like the prevailing interest rate environment, credit quality of the issuer, and the remaining time to maturity. Let's assume that 1 year after issuance, due to a fall in the prevailing interest rate, investors now require a lower interest rate of 8% from this issuer to convince them to invest in this bond. The market discount rate for the bond is therefore 8%. Now, if 8% interest is sufficient for the investors, the fixed coupon rate of 10% for the bond will drive investors to buy it, thereby pushing up its price. Investors will continue to push the price up to the point where the yield of the bond equals the market discount rate of 8%. Again, this price can be calculated if we use the market discount rate to discount all the future cash flows back to their present value and sum them up. Using the same calculation methods, we get a price of $1,066. We say that this bond is trading at a premium because its price is above the par value. Let's assume that in the next year, the credit quality of the issuer fell drastically due to an accounting scandal. The market discount rate rises to 12%. This time, why don't you try to calculate the price of the bond when the market discount rate of the bond is at 12%? You may pause the video now to calculate using either of the two methods we've discussed earlier. And we're back. Again, discounting back all the future cash flows by 12% and adding them up, we get a price of $952. This bond is described as trading at a discount because the price is below par value. Here's a summary of the relationships. When the market discount rate is equal to the coupon rate, the bond is priced at par value. When the market discount rate is less than the coupon rate, the bond is priced at a premium above par value. When the market discount rate is greater than the coupon rate, the bond is priced at a discount below par value. This means that there's an inverse relationship between the market discount rate and the price of the bond. Let's go back to our example. Thus far, we've been looking at annual pay bond to simplify the calculations for our understanding. However, semi-annual pay coupon bonds are the more prevalent type of bonds in the market. So, if this bond actually pays out coupons semi-annually, How do we adjust our calculations? The bond pays coupons of $50 every half a year instead of a full year. The principle for calculation is the same. Discount all the future cash flows to the current period. Note that the discount rate per half a year is 6%, half the market discount rate of 12%. Add up all the cash flows and we get a price of $951. By now, you should be convinced that the TVM calculator is the fastest way to calculate. Punch in the figures, noting that the number of periods is 6 half years, interest per period is 6%, and the payment per period is $50. You should get the same figure of $951. So far, we've used a bond's future cash flows and an assumed market discount rate in order to calculate the price of the bond. In a liquid market, where a bond is publicly traded with a known market price, we can use the price to calculate the precise yield to maturity of the bond based on this price. So let's say another year has passed and the bond's market price has dropped further to $932. Using this market price and what we know about the expected future cash flows, let's calculate the yield to maturity of the bond if an investor buys the bond at this point. Using the same discounted cash flows method, we equate the present value of the future cash flows with the current market price. The unknown here now is the discount rate R. You probably wouldn't want to solve for R using this method. Rather, simply bring out your TVM calculator and enter these parameters. N is 4, as there are 4 half-year periods left to maturity. PMT is 50, and the PV is the current market price of $932. Remember to key in the negative sign, as it is an outflow of cash from the investor. FV is the maturity rate of $1,000, and we solve for IY, which turns out to be 7%. Remember, each period here is half a year. Yield to maturity is an annual rate, so we have to multiply it by 2. So here we get a yield to maturity of 14%. This means that if the investor buys the bond at this point, at the market price of $932, the annualized rate of return to the investor is 14%. However, there are some critical assumptions to bear in mind. The investor will only realize the 14% yield to maturity if the bond is held to maturity, the issuer does not default on any of the scheduled payments, and the investor is able to reinvest coupon payments at that same yield. We've determined earlier that the price of a bond and its market discount rate, or yield to maturity, have an inverse relationship. When the price goes up, the yield comes down, and vice versa. There is another more subtle relationship between the price and yield of a bond. If we plot the data points that we have, we find that the relationship is not just inverse, but that the price-yield relationship is convex. This means that the percentage decrease in value when the yield increases by a given amount is smaller than the increase in value when the yield decreases by the same amount. Besides the inverse and convex effects, there are 2 more effects that we shall discuss. Before we proceed, it's time for you to test your understanding. Back to our example. 5 years before this bond was issued, this same issuer issued a 10-year, $1,000 par, 20% fixed coupon, semi-annual pay bond. This 10-year bond is scheduled to mature on exactly the same date as the 5-year bond. Assuming that all other factors are the same between the 2 bonds, calculate the fair market value of the 10-year bond at the end of the 5th and 6th year of the bond, where the market discount rate is 10% and 8% respectively. Pause the video now to work out your answers using your TVM calculator. And we're back. At the end of the 5th year, the number of half years to maturity is 10. The market discount rate is 10%, so the interest per half year is 5%. Payment is half the coupon rate of 20%, which is $100 per payment. Future value is the maturity value of $1,000. Solve for PV, and we get a fair market value of the bond at $1,386. One quick way to check is to look at the coupon rate versus the market discount rate. Since the coupon rate of 20% is higher than the market discount rate of 10%, demand for this bond will push the price above the par value. And at the end of the 6th year, everything remains the same except that there's now 8 half years to maturity and that the market discount rate has dropped to 8%. We get a fair market value of $1,404 for the bond. Now you may have noticed something. For both the 5-year and 10-year bonds, the market discount rate dropped by 200 basis points. In the case of the 5-year bond, the price goes up by 6.7%, whereas for the case of the 10-year bond, the price only went up by 1.3%. Here we introduce the third factor that affects the sensitivity in price when the yield changes. We call this the coupon effect. For the same time to maturity, a lower coupon bond has a greater percentage price change than a higher coupon bond when their market discount rates change by the same amount. Back to our 5-year bond example. Let's say that the market discount rate of the bond remains at 14% after the 3rd year, all the way to maturity. Would the price remain constant at $932? If you use TVM to calculate the price all the way to maturity, you'll find that the price will converge back to the par value of $1,000 even though the yield has not changed. This conversion to par value at maturity is known as the constant yield price trajectory. Regardless of whether the market discount rate is above or below the bond's coupon rate, the price always converges to the par value. This is because the par value is repaid to the investor at maturity. And this brings us to the 4th factor that affects the price sensitivity of a bond, the maturity effect. Let's draw another trajectory for another market discount rate of, say, 18%. From this graph, you can easily see the effect that the time to maturity has on the price sensitivity due to a change in market rate. Generally, for the same coupon rate, a bond that is further from maturity has a greater price sensitivity to a change in market discount rate than a bond that is closer to maturity. Before we conclude this lesson, let's go back to our example at the beginning. For what we've learned about pricing bonds using the discounted cash flow method so far, we use the same market discount rate for every future cash flow. A more fundamental approach, however, is to use a sequence of market discount rates that correspond to the cash flow dates. These are called spot rates. If we isolate the cash flows, each of them can be viewed as a zero coupon bond maturing at the date of the cash flow. The spot rate can be viewed as the yield of the zero coupon bond. This is perhaps the more precise way of determining the price of a bond, as we know that the discount rate for zero coupon bonds with longer maturities tends to be higher. So, for example, if we know the spot rate for X is 10%, Y is 11%, and Z is 12%, we can use the discounted cash flow method to calculate the price of the bond, which is $955. Note that you can't use the TVM calculator for this, as the discount rate for each cash flow is different. However, you can still use the TVM calculator to calculate the yield to maturity of the bond. Plugging in the figures, we get a yield to maturity of 11.9%. Let's conclude this lesson with an exercise. A 6% semi-annual coupon bond has 2 years to maturity. Calculate its price and the yield to maturity based on the following spot rates. Pause the video now to work out your answers. And we're back. As this is a semi-annual coupon bond, each period is half a year. Remember to divide each of the spot rates by 2 to get the appropriate discount factors. Also, par value is 100. The coupon per half a year is half of 6%, which is $3 per period. So the 4 future cash flows we have are $3 for the first 3 periods and $103 at maturity. Discounting all the future cash flows by the appropriate discount factors, we get a price of $94.82 for the bond. To find the yield to maturity at this price, we use the TVM calculator. Plug in the figures, and we get a yield of 4.44% for each period. To get the annualized yield to maturity, simply multiply this by 2, and we get 8.88%. And that concludes this lesson on pricing bonds. See you at the next lesson, where we shall study how bond prices and yields are quoted and calculated in practice.